All right, in this section, we're going to talk about chi-square distribution and test for independence. This corresponds to section 11.1 and 11.3. So this is part of hypothesis tests. So far, we tested for mean and proportion. Here, we're testing something slightly different. Here, when we test for independence, when we try to see if the two categorical variables are independent or not. Again, back when we talk about probability, the concept of independent is that one event affects the probability of the other, right? The other. Independency means one event doesn't affect the probability of the other, then two events are independent, otherwise they are dependent. So we're going to kind of do hypothesis testing on that. And another way this is slightly different than what we talked about before is we're not using z-score, we're not using t-score. We have a new distribution called chi-square distribution. It's spelled C-H-I, but it's pronounced chi, so K-A-I. And it's written, it's a Greek letter. It's written like x squared. So it's written like this. It's pronounced chi. It's spelled C-H-I. I know it's kind of weird, but that's what it is. So what's going to happen is once we get the sample data, we're going to put it in contingency table, sometimes known as two-wave frequency. So table that displays the sample values in two different factors. They may be dependent or contingent upon one another. So you can think of two variables that might or might not be affecting each other. So let's talk about property of this thing, chi-square distribution. Again, this is something new. This is chi-square distribution, chi-square distribution, chi-square distribution. You notice that we have few different graphs that have different shapes. So you notice that none of them is like normal where things are perfectly symmetric. So you notice that it says symmetric. No, there's no symmetricity. It's skewed one way in some ways. Signs of values. You notice that before when we had z-score, we had a negative z-score, we had a positive z-score. Here, you see how there's no negative side to the graph, right? It starts from 0 and it's all positive. It starts from 0 here, all positive. Same here. So in terms of signs of values, no negative chi-square values. The reason is because it's slightly theoretical, but when you calculate this chi-square value, we're squaring numbers. So when you square negative, all the negative becomes positive. That's why there's no negative values. Again, another property is that you notice that for different degrees of freedom, there's a df. This is df2, degrees of freedom 2, 4, and 6. We have different shape of graph. So that's another different property of a chi-square distribution. When degrees of freedom is 2, it's like that. When it's 4, it's like this. And when it's 6, it kind of looks more normally, except it's skewed, right? So here for different degrees of freedom, freedom means different graph. And as you can see, when degrees of freedom gets larger, graph becomes more normal. So when n, I'm going to change to degrees of freedom, gets larger, the graph becomes more normal. So these are just some properties of the chi-square distribution. And next, I want to go over some of the notations. So basically what's going to happen is when we do testing, our sample is going to come in the contingency table here. So you'll notice that there's like a bunch of rows, bunch of columns. There's an industrial sector variable, and there's year variable. So let's go back here, look at the terminologies. So R is the number of rows, C for number of columns, and O for observed values. This is basically what we get from the sample So this is a contingency table we get. Basically, it comes from the sample. From the sample is number of expected values, expected number of successes, assuming the rows and columns are independent. So basically what's going to happen is we're going to assume these two variables are independent. We're going to calculate this thing called expected value, compare it with observed value. If they're independent, observed values and expected values should be pretty much the same. And basically the hypothesis test is going to test for that. All right, so in our test for independence, we're testing whether there is a significant difference between observed and expected successes. In our contingency table, basically this is our sample, right? Using the test statistics, chi-square, this crazy stuff. Fortunately, we'll be using calculators, so we'll be using calculator like in practice, unfortunately, so you don't have to deal with this formula too much. All right, let's look at the next here. For the test for independence, the null and alternative hypotheses are always. So one nice thing about this is H0 and HA are pretty much fixed. So H0 is chi-square is equal to 0, which means independent. And again, of course, the alternative hypothesis is opposite of that, so not equal to 0, dependent. However, I'm going to make a little side remark. Because as we mentioned before, chi-square there's no negative chi-square. So when it says chi-square is not equal to 0, not equal to 0 means either it could be negative or positive, but there's no negative chi-square. So it basically says chi-square is equal to positive. In this case, it kind of works this way. So number 4, how do we calculate the expected number for entry in a contingency table by hand? This one is the row total times the column total over grand total. Where does that come from? Number 5, how does the formula for the expected number for entry use the null hypothesis in this calculation? Again, we're assuming the null hypothesis means that they're independent, and one of the property of independent event is probability of A, and B is equal to probability of A times probability of B. So basically it kind of works like probability A is like a row total, probability of B is the column total, so we're kind of multiplying it. So basically this formula is the application of that to our situation here. So far these are very like theoretical stuff, but how do we actually calculate that with our calculator? So this is practical version of what we're doing. Let's see, we have new calculator function key. First, this is how we're going to input the contingency table. This is going to be something new. We haven't done this before. So what we do is we're going to go to second. We'll do x to the -1 power. This is called matrix. Again, matrix just means like a box of numbers, basically a number table, right? Since contingency table, we have matrix. So we'll use second x to the -1 power, which is matrix. When you go there, it gives you different options. You can have matrix A, matrix B. So let's make a little side note. Instead of list L1, like L2, so on and so forth, here we have matrix A, matrix B, and so on and so forth. So once you go there, you kind of have to input the dimension. So if it's like 2 by 2, that means like I have 2 rows and 2 columns. If I have 2 by 3, that means you have 2 rows and 3 columns. So it depends on how your contingency table is given. I'm going to select those numbers, the dimensions, so I can adjust the size of the matrix, which is basically the table. All right, let's look at number 7. It says tests for independence are always what tail. Again, as I mentioned here, HA determines the tail is not equal to, but in here practically is basically bigger than 0 because there's no negative. So this is going to be the right-tailed. Here it's going to be right-tailed. And the degrees of freedom is going to be number of rows minus 1 times number of columns minus 1. Okay, now let's look at actual question here. Looking at number 9, it says sample of 300 students is taken. So I'm looking at this contingency table. Notice that we have the honor or not honor variable, and there's like your major variable. So I want to see if the being an honor roll and being music major or not, I want to see they're independent. So this is actual data. These are just to indicate the total. So I'm looking at this. It says 300 students are surveyed, so that's going to be my grand total. So it's there. What else do they say? Out of those, 50 are music student. So music here, the total of 50, and then 250 are not, so it's over there. Because there are 300 total, so 50 plus 250 will be 300. Also, it says 97 are honor roll, so honor roll total will be 97. That means the rest 203 are not. 203 is given to me, but if it was not given to me, I could still figure out because it'll be just 300 minus 97. All right, so part A, assuming they're independent, basically they want us to find the expected frequencies there. Again, here I'm going to write the expected values or frequencies. We can get it by row total times the column total divided by the grand total. So let's look at the music honor section here. So honor, the row total is 97. Music column total is 50. So in order to find the expected number, I want to do the row total 97 times the column total 50 over the grand total 300. And when you calculate this out, you get 16.2 if you round off. So basically I'm expecting to get about 16 people in this section. Let's look at honor and not music, this part, this cell. So again, we'll do row total versus column total. Now the column total is going to be 250. So 97 times 250 over 300 will be 80.8. So that's what I expect to have in this cell. Here, I'm going to have you pause a little bit and figure out the next two cells, expected value of these. All right, so I got 33.8 for this one, and then 169.2 for this one. So this is what I expected to get if these two things were independent. Honor versus the music major. Now I actually look at the observed value. Let's look at what I actually got from the sample. So here, part B says, assume there are 22 music students. So I'm going to write it in blue. 22 is my observed value. So this is what I got from the sample. So I was expecting 16, I got 22, so it's slightly more than what I expected. So basically what we're going to do eventually is I want to see, like, is it way different or is it not too different? If it's not too different, then basically they're going to be independent. If they're way different, then there's no way this is going to be independent. So let's keep that in mind. How do I figure out the observed value for honor, if the music major? I know there's 97 here, so basically 97 minus 22 will get you the answer. That'll be 75. I can kind of do the same argument. Here will be 28, and then here will be 175. All right, so how do I actually test it? Here, they want us to do it by hand, but here we're gonna actually use calculators. So we'll do, as I said before, I wanna go matrix, so second, x to the negative 1 power, which is matrix. And then I'll select the matrix A. Here I have 2 by 2 matrix, 2 rows and 2 columns. I'm not counting the total, I'm just counting actually my data. So it's going to be 2 by 2, 2 by 2, and I'll input the observed value, just like this. So here, input the observed value. Basically input the sample. Makes sense. Input the sample. Here we calculated the red number's expected value ourselves, but in practice the calculator is going to do it for me. So here I just wanted to show you what the calculator does, but in practice calculator will calculate it automatically. So in order to test this, we'll do stat, and then we'll go to tests. Again, this is a new test function key. So we did z-test, we did t-test, it was one prop z-test, we did a lot of different tests. We scroll down, we're gonna choose option C for this one, chi-square test. This is a new one. And it basically asks for observed value, observed matrix. So we already inputted in A, so it's there. It'll say expected B. I don't have to do anything. Don't have to input B. It'll do it for you. Notice that they didn't ask for H0, HA, because H0 and HA are always fixed. They didn't ask for which tail because it's always the right tail. So basically all you have to input is just matrix A. So I'm gonna make a side note here. This is all you need. All you need. So in some sense this is a little easier to input because there's only one table you have to input. So when I calculate the p-value, it's gonna give you, scroll up a little bit, the p-value is gonna be 0.053, which is just over alpha. So p-value is not small, so that means our sample is not unusual. So we fail to reject H0. So everything else is pretty much same from here. I reject the sample that is unusual. The sample happened to be not unusual, so I'm gonna fail to reject H0. And our claim was, we're testing if they're independent, so claim is basically H0, so I'm gonna just say the same thing. So we failed to reject the claim. So my final conclusion is we don't have sufficient evidence to reject the claim that the music major and the honor roll are independent. That's it. All right, I'm gonna have a pause and work on number 10. I think that's the end of the worksheet.